Sorry, I should have come to the technical check. Right. Hello. Thank you for being here. This is one of those papers where the title is also an accurate description of what's going to happen. So let's begin. We're combining dependency grades and adjoint logic. So at this point, I mean, we've had a bunch of talks about dependent types already, but the main sort of gain is we get expressiveness, we gain verifiability, but this comes at a big price, and that is that inefficiency can sometimes be almost baked into the language. And let's look at an example of what this means. So let's consider just a very simple dependent type of vectors, of elements of some type of length n, and a push constructor which takes an element in the vector and produces a new vector. And if we look at this type, the type signature is actually not complete. Well, because we have this A and we have this N, and so they need to appear somewhere, presumably. And so we write this. Okay, that's fine. But now, what are these A and N? They appear in a type signature and they're arguments to our push, but they're unused. And then, furthermore, this is probably a functional language, so the output is probably going to be a copy. So our push function runs in linear space and time, which is not great. So we wanted to address both of these issues. And how are we going to do this? Well, for the unused variables, we're going to add grades into our type system, which can account for how variables are used, and will allow us to optimize unused variables. And then to do in-place updates, well, if we treat our values linearly, then, well, once we've used it for the push, then actually we can't use the vector again, and so it's fine to update it in place. And so that's what we did. This is our main objective, is to integrate dependent types, grades, and linear values. And this is based on Krishnaswamy et al., where they combined just intuitionistic dependent types and linear types. And furthermore, Choudhury et al., which is a graded dependent type system. There are others, but we use this one as our basis because, well, my advisor co-authored that paper. So let's look at the graded type system. And this is, by the way, exactly the same as this one, with one tiny modification. So let's look at the graded type system. So we can control variable usage, and then I just wanted to give some examples of what we can actually control with this. So we can do relevance analysis like we saw before, so we can check are these variables actually used or not, and this allows us for some optimizations. We can also do automated garbage collection, so you can assign some number of uses to a variable, and then once it's used up, you automatically know it's gone, and you don't have to do any like counting or anything. And then there's also things like data flow control, where you can tag variables as high or low security, and you can ensure that high security things don't leak into low security contexts. So this is our judgment form, and if you ignore this first part before this O dot sign, then this is just a judgment with assumptions and a conclusion. And these RIs here, they indicate how these assumptions are used. So R1 indicates how X1 is used, R2 indicates how X2 is used, and so on. And they are all drawn from some semi-ring R, and basically your choice of semi-ring is what dictates which resource you're tracking and how you are accounting for it. So I want to show some rules for you to get a feeling about how this type system works. So first of all, we do have weakening, and essentially this says, well, okay, so delta is the resources. This little delta is is the resources that are used to construct this T. And then if we can introduce introduce an unused variable, but we have to use it at grade 0, which I think makes sense. If you're not going to use it, you should put 0. We have a sub-usaging rule, which essentially allows us to say, well, if we have some resources, if we use some resources to construct T, then we can use more resources. So we can be wasteful if we so choose. And finally, this is a variable rule. Here's a variable rule. So if we have any type, then we can use the variable of that type at grade 1 to produce an identity function. And here there's actually something interesting to note. And that is this delta here references what resources are used to construct this type capital X. But this delta is gone here. And so actually these judgments do not contain any information about how the type was constructed. They only contain information about how the term is constructed. And then finally, one more rule, which is just I chose function application just to see how other rules interact. And here, so we have a function and a potential argument. This annotation here says that the argument is used at grade R. So if you were to uncarry this and move this thing into the context, you would have an R here. And then, so basically this is just about showing how these grades behave. Well, we need to compute F and T individually, which explains this addition. And then T is used at grade R, so we do a scalar multiplication here. Okay, so now we introduce a mixed fragment, and this is essentially we just say, okay, we have these graded things, and now we're going to just also have linear types, and the conclusions are now going to be linear terms, and we now have this annotation M, which stands for mixed, on our turnstiles. And this behaves essentially just like ordinary linear logic. So this is just the ordinary function application rule from linear logic. And then we just also have these graded assumptions that are just present throughout all of these judgments. So this is the actual rule. And so we have a fixed context delta of graded assumptions. And the grades here are added together because we need to compute both things in parallel. So very briefly, we have modal operators that connect these fragments. These are essentially, as in Krishnaswamy's thing, except we have to make things graded in the correct way. So this F operator takes a graded term and makes it into a linear one, and it functions essentially like a dependent pair type, where the first component is graded, the second component is linear, but then the whole pair is also linear. And then for this, the other one, this takes a linear type and produces a graded type. And the terms are, in a good sense, the same, so between A and G of A. And we have a good notion that linear usage corresponds to grade 1. So now let's look back at our example. So now we can say, well, okay, this A of type and this N of type natural numbers are going to be both graded at 0. And then furthermore, we're going to make these guys here linear. And so now we have a push function, and we can correctly say that these are unused, and we can correctly say that these will be consumed by pushing, and we can do an in-place update. So from here, we have now a thing that looks like linear nonlinear logic, except one of our fragments is dependent and graded instead of just intuitionistic. And we wanted to generalize this to look a little more like adjoint logic, where we don't just have a intuitionistic and linear, but we can have potentially many different things. So let's recap what adjoint logic is. So in adjoint logic, each proposition comes with a so-called mode. Each mode has a set of structural rules which it admits. So it admits either weakening or doesn't admit weakening. It admits construction or doesn't admit contraction. And the preorder that the modes are arranged in is compatible with this set of structural rules, in the sense that if one mode is bigger than the other, then its set of structural rules is also bigger than that. So this is what a judgment looks like, and essentially these are just assumptions. They have their modes annotated, and then we have a conclusion with its mode annotated as well. And there is a constraint which says that the mode of the conclusion has to be strictly or less than or equal to all modes of the assumptions. Now, in our system, we keep this idea of having modes that are arranged in preorder, but now we have the semirings, which account for grades in the structure. And so essentially now every mode comes with a semiring, and this inclusion of structural rules has been replaced by having a homomorphism of semirings. So now, just briefly, I'm going to explain the judgments. The rules are actually the same, exactly the same as in the graded fragment from before. The fact that this has now different modes and that these are now different semirings actually does not answer the equation at all. I mean, syntactically, there is a notational convention, but other than that, they look the same. And so now we just, in addition to having, so if you forget about this vector of these Fraktur m's here, then we have the judgments from before. But now these m's just also indicate which mode the ri's are from and which mode the variables are from. And we still have the same constraint. And this is actually now important for some of the scalar multiplications to be defined. So one thing that we also wanted to do is we still wanted to gain control over contraction and weakening. And for weakening, this you can do it, okay? So you just have a predicate that's called weak m, and okay, like if weak m is true, then you can weaken and you put 0 and it works the same way as before. But controlling contraction is actually a little more difficult. And this is mainly because of the dependency. So let's look at this hypothetical dependently typed function application rule again. So we have a function and we have a potential argument, and now we want to say we apply it and we concatenate these contexts. But the problem here is that we really should check that this little a is actually correctly of this type, capital A. And it's actually just kind of unclear what that means when they exist over different contexts. And so implicitly, well, this should just be one context, and we should implicitly contract both of these contexts together. And that gives us some implicit contraction in dependent type systems if we set them up sort of in the obvious way, let's say. And so this actually also enters with the grades, and it's unclear how to handle contraction. So on some meta theory, we actually have graded contractions in both systems, so we can actually not control it. We proved substitution for both systems, and only for the former one, we developed some operational semantics and we proved subject reduction. And with that, I feel like I just took 5 minutes. But with that, I'm done. Thank you, and questions.
I have plenty of times for questions.
So this is a really nice talk. One thing that was a little bit unclear is about the status of contraction. Could you go back to maybe slide 25 where you talked about the problem? And it wasn't clear whether you have come up with a solution or not.
No, so essentially, if you want, sort of in the naive way, you would have these contexts both be the same.
Yeah.
And you put just one gamma here. Mm-hmm. And that is sort of the reason why there's some implicit contraction in dependently typed systems, sort of by default. And that also enters for us, and so we haven't figured out a way to control it.
Okay, so this is an open problem that you don't have a full solution. Yes,
and so we imagine if this weren't dependently typed, we could just do it by just adding a predicate and just saying there's no contraction in this mode. Mm-hmm. But now, because, well, in this case, we just can't.
Okay, thanks.
Hi, yeah, thank you. Thank you for the talk. A bit of a motivational question. You have grades, modes, and linearity. What are they used for? Like, what's the difference in? Can you give some intuition as to that? Like, why do you need all three?
So I wish I knew what exactly you're aiming for, but so.
What kind of language do you want to build using this?
Because they all, to me, they serve similar purposes. They're tracking how variables are used, and you can sort of use one to approximate another in a lot of cases. So that's why I'm kind of asking, what do you get from having these three of them combined? And if you don't have an answer, that's okay.
So in reality, I'm very bad at philosophical, like, motivational things. And so I don't at least have an answer right now. I'm very sorry. I come sort of more from the theory side. And okay, thank you.
I think I know the answer to this question, but I think it might help with your other one. So you used the linearity to let you were doing reuse, right, or free or something similar. Like you're in your setup. Why could you not do that with why is the grading not sufficient to do that? Right? Like you have something you know that the thing is at grade 1. Why is that not sufficient to do reuse?
See, this is really embarrassing, but
I mean, I suspect
I'm sort of really the wrong person to ask for.
I suspect
for practical applications. I suspect this is a distinction between linearity and uniqueness, but Oh, okay. We have, I have something. So we had a, no. Here, 1, 2, we have this rule. So this is actually, so this says you can be wasteful. And so, okay, the semi-ring comes with a pre-order that I haven't mentioned, but it appears here. And so essentially, if, let's say you have 0 less than equal 1 in your semi-ring. If something is greater than 1, and you have 0 less than equal 1, then it might be used, but it might not be because it might have been obtained by applying this rule. So it might, so actually you get affinity. You get something that's affine. Whereas in linearity, you know for sure it's greater than 1. And it's really used once, and so there are some differences here. Similarly, if, so you get fewer guarantees. Similarly, if 1 is less than or equal to some other element, right, then you can say, oh, I allowed this potentially, this is potentially unrestricted, but it might still be linear. So you get some slightly different things from this.
Yeah, that makes sense.
Okay. I hope that was maybe helpful as well. I hope like
questions about motivations.
What does the regularity property of your language look like? Because I'm just wondering, like, is there any, like, does your usage tracking also apply to the type, or is it just at the term level?
So in constructing the types, we carry these grades around, but no, the resource tracking is sort of, in this judgment, this delta, all of these really just describe how the term is constructed.
So it's similar to grad, where when you check the type, you use
It is actually exactly grad.
Okay.
We reuse the type system, basically.
Okay, that makes sense. Thank you.
I quite like the presentation you had just simply of adjoint logic in the way you showed it here. And I was wondering what your preferred definitive resource is for that version of a presentation of it.
I don't know. That's just kind of how I read that paper, and that is sort of the notes I took for myself mentally. And
From the paper that you cited earlier.
oh no, this adjoint. Oh, so there's a paper that's also just called Adjoint Logic.
Okay, there's a lot of papers called adjoint logic.
Oh, is there? Okay. Oh, oops. Embarrassing. Who are the authors? If only. I don't know the authors off the top of my head, but surely someone in the audience knows. Which one am I? Yeah, Jason. I was gonna say Jason Reed is like one of the names, and there's more, but I don't remember who they are at the moment.
That's fine, thank you.
Is this one paper online by class principal living charge?
Yes. Yes.
It's exactly it.
That's the one I'm referencing.
One question.
Could you go back to the slide with the type formation premise, where it was that one.
Okay.
So I have a question. How does this affect like the formation of equality types? Because
We don't have those
okay,
for now. We actually don't have any inductives for now. This is just a core type system.
okay, thanks.
Thank you.
Then maybe you can speak a little bit.